y simple and x simple case. Any questions? Okay, so next I want to concentrate on the z simple case. And I want to mention the following, which we already did the examples before the spring break. Let's see if you can still remember that. So in the first step, in the very first step, I peel off the z variable, which means we already decided the interior integral is with respect to z. And then I need to identify the double integral with respect to x and y. We can do this by y simple and x simple identification. We can also identify this region as a polar region, all right? So we did do that. We can identify this region as a polar region as well, which means we don't need to use x simple or y simple identification anymore. We can also do a polar rectangle or a R simple region, all right? So if you're doing that, instead of having x and y, I have from alpha to beta, from A to B. Okay, so I'm still looking at this triple integral. I want to identify R as a polar rectangle. Okay, so a polar rectangle means R is equal to R theta, where R is bounded between A and B. Theta is between alpha and beta. Okay, so I have two numbers for the radius, I have two angles for the angle theta. Okay, so I can also identify the region R as a polar rectangle, which means theta varies from alpha to beta, R varies from A to B, and I need to switch between x to y and R and theta in everything. Right? So I need to write down these variables in x, y to in R and theta. I also want to change these two functions from x, y to R theta as well. Okay? So the relation between x, y to R and theta is x is equal to R cosine theta, and y is equal to R sine theta. Okay? Again, if you feel this is too quick for you, I urge you to talk to me after class. Okay, so I have office hour. We can always schedule some other appointments. We can always talk, and let's see if you have some individual difficulty understanding what's going on here. Okay. So what I'm doing here is I'm simply changing x, y to R and theta, regardless of what z is. I don't care about z. Okay, this is purely about x, y, and R and theta. So I keep G1 R cosine theta, R sine theta, G2 R cosine theta, R sine theta, and F is R cosine theta, R sine theta. I don't care about z, so z stays here. Okay, and then from dx dy to d r d theta, I need a r here. So r dr d theta. So this is going to be z simple in the space polar on xy plane. Okay, you can write down the factor r inside of the integral of dz or outside of the integral of dz. It doesn't really matter. Okay, because this integration is with respect to z. R is always regarded as a constant. Okay, R is always regarded as a constant. So if it is a constant, you can pull out from the integral directly. Yeah.
Can you also do it if they give you like a y simple or like an x simple, where you have instead of like x and y being r cosine r sine, you can do like a z and y where it's like r cosine and
yeah, you can do that. Okay. Yeah. So what she is asking is actually, if it is y simple, I can also identify xz region as a polar region as well. Okay, that's a very good observation. I can also do that with respect to x simple in the space. So for yz region, I can also identify it as a polar region. However, there's another way of understanding what this is going on here. If you want to do that, you can identify this yz region or xz region as a polar region. The other one you can understand is you can rotate the intergradient region in x, y, z space to the direction that z is always the one you single out in the very beginning. You only need to deal with the x, y region as a polar region. Okay, That's another way you can understand what's going on here. Okay, but to make it simple, I'm only going to look at this only case and identify it as z simple in the space, polar on the plane. Okay, polar on the plane. And this formula seems a little scary, but in application, it's really quite straightforward. Okay, so here is my example. I have a triple integral from 0 to 9, from 0 to square root of 81 minus x squared, from 0 to square root of x squared plus y squared. And the intervening function is x squared plus y squared to minus 1/2 dz dy dx. Okay. So in the very beginning, I want you to quickly understand what this triple integral is in terms of the identification we had a couple of minutes ago. If I have this intervening order dz dy dx, this is z simple in the space and y simple in the plane, right, on the xy plane. So that's why I have two functions involving x, y to define z, and two functions involving x to define y. All right, I only need two numbers for x. Okay, so this is the z simple in space and y simple on the xy plane. So because the polar are occurring in this formula is called a cylindrical coordinate system. So this is a triple integral in cylindrical coordinate. Okay. So I don't even want to call it cylindrical. It doesn't really make that much difference. Okay, I don't want to scare you of introducing another coordinate system. So if we decide to call it a cylindrical coordinate system, you should always keep this in mind. It is nothing but a z variable plus a polar coordinates. Okay, it's just z variable you stay as what it is, and then for x, y, I use r and theta. That's all. It's up to you. You want to call it cylindrical? It's up to you. But it's just a z simple plus a polar on that plane. Which means if I want to use this system, it's basically just to use a polar coordinate system, all right? It's basically just using polar coordinate system. Remember, when we're dealing with double integrals, in which cases the polar coordinate system is much easier than xy. Yeah. I give you the hint. Especially if you see these kind of terms, right? If you see x squared plus y squared, go for polar coordinate system. This will make the triple integral much, much easier. You can switch between x squared plus y squared to r squared, right? So you use the formula x squared plus y squared is equal to r squared. Use the formula to transfer between x, y to r theta. If you have x squared plus y squared, go for polar. Okay, that will make the problem much easier. And in this class, they want to test you about cylindrical coordinate system or polar coordinate system, especially for this kind of examples, right? They particularly design this kind of problems for you to use this coordinate system. So just waste no time. As I said, as long as I'm using a cylindrical coordinate system, it has nothing to do with z. That was me. It has nothing to do with z. So you don't have to worry about this interior integral at all. You don't have to worry about that. The only thing you're doing is to identify the double integral region right here, originally with respect to x, y to r and theta. That was me. So keeping this in mind, this is going to save you a lot of time and energy, and also you will be pretty clear about what we are doing here. I don't care about what's inside of the interior. The dz variable doesn't really matter to me. I'm only looking at the x and y, and I need to identify this region on xy plane. Especially, a lot of people try to switch between x, y, z variables to cylindrical coordinate system by drawing the picture in R3. It's pretty challenging here. So if you look at this integral, if I ask you to draw this triple integral intervening region, it's pretty challenging, right? Yeah. It's pretty challenging. You have to give me a solid region in R3 about these relations. x is bounded between 0 and 9, y is between 0 and this function, z is bounded between 0 and square root of x squared plus y squared. You identify this region and other three is not easy. But if I don't care about the interior, I'm only looking at this region on xy plane, it's much, much easier. Are you with me? It's much, much easier. Where x goes from 0 to 9, so 0 to 9 here, and y goes from 0 to square root of 81 minus x squared. But we have dealt with this so many different times. Y equals square root of 81 minus x squared is only a piece of a circle, right? A piece of circle. And which piece of the circle is depending on the restriction on x, right? So y squared plus x squared is equal to 81. So that is saying this is a circle with radius 9, right? So y equals square root of 81 minus x squared. So x squared plus y squared is equal to 81. So I have a circle with radius 9. But x goes from 0 to 9, which means I'm only looking at a quarter of a disk. All right? Do you agree with me? I'm only looking at a quarter of a disk. And this identification of a region on the xy plane is so much easier than writing down and graphing this region in R3. So keep in mind, when you are trying to translate between this into a cylindrical coordinate system, do not care about z. Never make your z into the loop. It's going to make your work much more harder. Okay, just look at xy. So xy is in this region, which means if I identify this quarter of a disk in polar coordinates, it's going to be theta goes from 0 to pi half, and r goes from 0 to 9. Okay, so that will be much easier. So from 0 to pi half, from 0 to 9. And then now I look at the inside. I'm going to switch between x, y to r and theta. Right? So it's going to be from 0 to r. And what is this integrating function?
1 over r.
R to minus 1 or minus 1/2? Minus 1 or minus 1/2? You have to be pretty careful here. So x squared plus y squared is equal to r squared. So this is actually r squared to minus 1/2. So you're actually getting r to minus 1. Am I right, Brett?
Yes.
Yes. And then dz. I'm going from dx dy to dr d theta. I have r dr d theta. Okay? And immediately you see this is a much easier triple integral, right? This is a much easier triple integral, especially even you have z variable integration, because r and theta are both regarded as constants. So this is just a constant number here, right? So it's r minus 1 multiplied by z. That's the antiderivative, and then evaluating from z equals 1, so z equals 0 to z equals r. R dr d theta. Okay. So like I said,
Thank you.
I usually keep this evaluation with the variables. Yeah.
Can we simplify before we actually do the, taking the antiderivative? Isn't r minus 1 times r is just 1, and then it's a lot easier for me?
Well, you can do that as well. Yeah, if you want. They are all regarded as a constant. You can do that as well. Yes. So from 0 to pi half, from 0 to 9, from z is equal to r, I'm getting a 1. Z equals 0, I'm getting a 0. So it's going to be r dr d theta. Okay? So then it's going to be from 0 to pi half r squared divided by 2, evaluating from r equals 0 to r equals 9. And d theta, let's see what we have. We have 81 divided by 2 multiplied by pi half. So it's going to be 81 pi divided by 4. Okay? So that's going to be the answer here. Okay, so as you probably realized, the most important step is this step. This is the key step. As long as you can translate between z simple in the space, y simple in the plane to a cylindrical coordinate system, the following work is extremely easy. And that's the pattern for all the double integral and triple integral. How to identify the triple integral and the double integral is the key part, right? The key part. And we don't need to have a super good drawing skill. We don't have to be super good in drawing solid region in R3. As this example shows you don't have to worry about that. Okay, but you do have to have a basic drawing skill on the XY plane. Okay, in terms of you have to at least identify where it is and how you can tell the key information. Right, you don't have to draw your disk to be super precise, but you have to be able to tell the key information here. Okay, yep.
I have a few questions. The first one, when you find R, it has like the last two integrals. It has to be solely XY plane. Okay, and then the second one is you just figure out what that is, and then you just plug it back into the Z to the DZ.
When I identify this region on the XY plane, I don't really care about the Z integral at all.
Okay.
But when I do that, I need to switch between XY, R, and theta.
Okay.
Right? And when you take the integral with respect to Z, R and theta are both constants. So this Z variable is really pretty dummy variable.
Okay.
Right? It's not going to play any role when you identify the region. Questions? Now I want to give you a slightly more challenging question. Only slightly. So let's see, we have this part. From 0 to 6. From 0 to square root of 2. From x to square root of 4 minus x squared. E to minus x squared minus y squared. dy dx dz. Okay? Questions? No, square root of 4 minus x squared. Oh, this is 2, square root of 2. Yeah, my z has a little bar here. Okay. So first of all, when I look at this double integral, triple integral, I have to stare at it for a couple of seconds, not too long time. I don't want to spend that much imagining. So I see x squared plus y squared right here. So I want to use a polar in the x1, right? In polar in the x1, that means